Good day and welcome to our 2018 webinar speaker series hosted by the International Society for Industrial Ecology. My name is Mai Ichihara and I will be your host for today's webinar titled Dynamic Material Flow Analysis with Python. The ISIE webinar series invites leading researchers from various fields to talk about the latest opportunities and developments in industrial ecology. In today's webinar, we will explore the basics of dynamic material flow analysis and dynamic stock modeling and introduce the open source Python library for dynamic stock models. Here with us is our speaker for today, Stefan Pauliuk. Stefan Pauliuk is an expert in method development to assess sustainable development strategies. His work includes supply chain analysis, scenario modeling for sustainable material futures, and indicator development for resource efficiency and circular economy strategies. Together with colleagues, he estimated current in-use stocks of steel and developed scenarios for material efficiency in the future steel cycle. He is an assistant professor for sustainable material and energy flow management at the Faculty for Environment and Natural Resources, University of Freiburg, Germany, where he leads the research group Industrial Ecology Freiburg. Before we start, I would like to remind listeners that we welcome any questions you might have, and I will direct them to our speaker at the end of the talk. Throughout the presentation, please type questions directly into the Zoom Q&A window, not the one labeled chat. And with that, we welcome Stefan Pauliuk.
Thank you, May, for introducing me, and hello everybody, welcome to this webinar. I'm quite happy to be part of this series, and you will also see how the content I'm presenting will link to the content presented by Oliver Czencic last week. This webinar will have three parts. We will first talk a bit about the background, why we do dynamic MFA and what are the main applications. We'll then have a run through the basic principles of dynamic MFA. And then for the third part, we will switch from presentation mode to the software and have a look at how it is then practiced with the Python library. So let's start with the big picture. To develop society, we need a lot of services. We need roads, we need houses, we need bridges, a lot of infrastructure, industrial capacity. And all of these items, products, they need materials. One of the most important materials are cement and steel, whose production you can see here. And we need a lot of them. For steel, production figures have grown to 11 million tons per day. And for steel, we are now at more than 4 million tons per day. And the production of such amount of resources to build up our cities globally and our infrastructure causes a lot of resource depletion, and for these materials in particular, carbon emissions. So steel and cement production alone are responsible for between 15 and 20% of global greenhouse gas emissions, just the production of these materials. And if we now look into the future, we will be more people, and the people in the future will also want stocks. They want cities, they want travel infrastructure, they want products, they want houses. And on this graph, the blue area denotes all the stocks that haven't been built yet. The red ones are the stocks and their embodied emissions in the rich countries, the gray one in the developing world and the global south, and the blue ones is all the material that isn't there yet. And just producing this material with current technology would emit another 350 billion tons of carbon dioxide into the atmosphere if done unmitigated and with current technology. And that is not sustainable. It would eat up already a third of the remaining carbon budget only for producing three materials, cement, steel, and aluminium, not mentioning driving, vehicle, or heating or cooling a home. So we really need to do something about our material use. And the first step would be, of course, a scientific assessment. We need to understand how material cycles develop over time, how demand evolves, how can we change demand, what are alternative scenarios, and how can we recycle, reuse, and use materials more efficiently in general. An example here would be a study of the global steel cycle, where we can see how material efficiency strategies, for example, more intense use, like car sharing instead of everybody driving their own car, or better use of office space, or the lifetime extension of products can change steel consumption and thus also emissions. And you see that the rapid implementation of material efficiency strategies can move emissions in the steel cycle from this more or less stable blue baseline, which is still unsustainable because it's at very high levels of carbon emissions, to a more sustainable or less unsustainable regime denoted by the red baseline, that could even bring the steel sector in line with the 2 degrees Celsius target. So the question is here, what are the methods that we need to develop such scenarios, and how do they actually work? So this is the topic of today's lecture. Another example is the so-called circular economy. When we talk about the circular economy, we need to understand how material circles move over time, because today's consumption will be tomorrow's scrap and tomorrow's potential for recycling and reuse. This picture here shows that the current global economy is not very circular. The flow that goes back into materials processing is quite small compared to overall consumption. And you also see that there's substantial stock growth. The addition to stocks is larger, about 4 times larger than the demolitions. Global stocks are still growing. That also inhibits circularity, and we need to understand how stocks will grow over time. Another application is indicator development. We need to understand how we can translate our material cycle understanding into practical indicators that can be used in the scientific debate, in the policy debate, and maybe also in policy making. One example here is the lifetime of materials in the anthroposphere. Many people think of metals having an indefinite lifetime because industry is very good at promoting that efficiency. Recycling is 100% efficient, but this is unfortunately not true. There is losses at all cases, all stages of the cycle. So material, even for very mature material systems like steel, declines over time. And we calculated that the average lifetime of steel that's currently consumed will be around 250 to 300 years until it will be lost in obsolete stocks, in landfills, or in slag piles. So also here, we need to understand how we can maybe change this picture and whether this is a useful indicator. So we're now switching from background to methods and want to learn how we can actually model such systems over time. For example, model the decay of metals or model the development of stocks over time. In material flow analysis, we always have a system definition. So we model the materials as flowing between processes or being stored in processes. And the only thing you need to convert a static MFA model into a dynamic one is to add the time dimension. So now we don't look at a 1-year snapshot of a material cycle. Instead, we look at time series of stocks and flows over time. And when you do something over time, the relations between stocks and flows becomes very important. And the model we apply to link stocks and flows is called the population balance model, and it is actually quite simple. We have an inflow of material, for example, a car that's being bought and put into use. And at the moment the car is being bought, it represents an inflow that's put into the stock. And then the car will remain in the stock for a certain time, and after the lifetime of the car has expired, the car will be sent as outflow to the scrapyard or to exports. And at any point in time, we can establish a mass balance or a product balance between inflow and stock flow and inflow, outflow, and stock change. For example, if the inflow is 5 cars, so we have 5 new cars registered in a certain street in a year, and the outflow is 2 cars because 2 cars were sent to the scrapyard in the same years, then the stock change in this road will be 3 cars. So we can formalize this relation between inflow and outflow a bit further by introducing what we call the impulse response function. I already talked about the lifetime, that we say everything that we will consume will turn into scrap 1 day later. And this turning into scrap can be seen as an impulse response. So the impulse is a consumption flow, here visualized by the peak inflow in the lower left corner. And the response of the system is that this input is stored for a certain amount of time, the useful lifetime of the product, and then gradually released as scrap. There's 2 ways of looking at this impulse response. The first one is a fixed lifetime. That applies, for example, to security-relevant products like fire extinguishers. They have a predefined lifetime, maybe 10 years, and after that, they have to be replaced. So they have a fixed lifetime, they're consumed today, and they're sent for recycling in 10 years from now. Most products don't have a fixed lifetime because there are many factors that contribute to obsolescence, like cars. Some of them are driven a lot, like taxis, so they get deregistered already after a few years. Other cars are hardly ever driven, so they may have a very long lifetime, or they end up as old timers. So for most products, buildings is another example, the peak inflow for 1 year, So the cars that are consumed this year will be distributed over time as outflow. Some cars will deregister earlier, some later, and we can define a lifetime distribution that is well known from statistics, that we say for each year we can assign a probability of the product leaving the stock. And if you sum up over all years in the future, the total probability that the product will leave the stock one day is 100%. Just that the probability is spread over different years. So in 5 years from now, maybe 5% of today's cohort leave. In 6 years, it's 8%, and so on. The stock model is a linear model over time, meaning that we can just add the contribution of different years. So if we have an inflow in the first year, it will create a certain outflow. And if we have an inflow in the second year, it will also create a certain outflow that's maybe time shifted. And to get the total outflow in the future year, we just add up all the contributions of the different age cohorts that were consumed previously. So this is one of the main principles. We have in every outflow a composition of many different inflows. So think about the cars that are deregistered this year. They consist of cars that were maybe built in 1990. They also consist of cars that were built in 2005. All of these historic age cohorts contribute to the current outflow. If you link it back to the mass balance, there's one last example where you can see the peak inflow in a given year. So that would be maybe this year's steel consumption. And then you have the impulse response. This year's steel consumption is added to stock and then slowly declines according to the lifetime model. This is shown in the lower graph. And the outflow is the derivative of the stock decline. So this is, in this case, a bell-shaped curve. This is proportional to the lifetime distribution. What do we do with this kind of modeling? Here's a good example of the estimation of steel stocks in industrialized countries. Steel stocks are not recorded in statistics, so if you want to know how much steel there actually is in the different countries or how much cement or aluminium there is, we need to estimate those numbers from models. And one of the models is to determine how much steel was actually consumed in different years, and this can be done from mass balance. We know how much steel was produced. We know how much steel was imported or exported, so the balance of it, the market balance, must have been consumed in the different countries. We call this the apparent consumption. And the apparent consumption is added to stock, but it also leaves the stock after a certain time. The buildings that were built 110 years ago, especially industrial or commercial buildings, most of them have gone already. The vehicles are gone after 15 years and so on. So we take the inflow, and for each inflow, we calculate with a lifetime model how much of that specific inflow from that year has left, and all the rest must still be in the stock. And this is the application of the lifetime model to estimate the stock. We call this the inflow-driven model because we have an inflow that drives the stock accumulation. The example here is for the steel cycle per capita in the United Kingdom and the United States, and you actually see saturation per capita. You see that on per capita level, the stocks have leveled out, indicating that there is a certain sufficiency level for steel stocks that is needed for an industrial country that can serve as benchmark for guiding the development in countries that haven't built up the steel stocks yet. And this is exactly what we did with the other type of dynamic stock modeling that I want to focus on today. This is the stock-driven modeling. So inflow-driven modeling means you know the historic consumption, and from this you estimate the stock with a lifetime model. In the scenario modeling, the stock-driven model, you do it the exact opposite way. And the reason is that stocks are a better proxy for the service provided to people than flows are. The service that people need is transport or housing or communication. And to do that, you need infrastructure, you need stocks. The stocks that are built up with all the steel and the cement that we saw pictures of earlier today. So we take the policy here, for example, of China to develop the countries within the next 20 years to a fully industrialized and developed country. And then we say, okay, for this system, you need a lot of stocks. Sorry, you need a lot of services, and to provide those services, the housing and the transport, you need stocks. And to build up and maintain the stocks, you need flows. So the idea of the stock-driven modeling is that you first start with a stock scenario. Here, these are the gray curves in this plot. The light gray curve is the per capita stock that will saturate at 10 tons per capita. This is the assumption taken from the historic studies. And the dark gray curve is the total stock, so the per capita stock multiplied by the population. It shows a slight decline in the second half of the 21st century because of the population scenario also containing a decline of the Chinese population. The question that we now ask ourselves is, what are the inflows of steel that are needed to build up the stocks and to maintain them over time? This is the stock-driven model. It is solved by a recursive procedure using both the lifetime model and the mass balance principle. The recursive procedure, we'll do it in example in a minute, goes as follows. We go year by year, and for each year we first calculate the outflow of historic years. So let's assume we are in the model year 2060. We calculate how much of the previously consumed steel in all previous year is leaving the stock exactly in 2060. This we do by applying our lifetime distribution that we showed before. And then we have in step 2 the mass balance gap. If the stock scenario says we should have 100 units of stocks, and our previous calculation said that at the beginning of the year we had 90 units of stocks, but we discard 5 units in the current year, so we have 85 units left. That means we need to consume 15 units to go from 85 to the target value 100. And we set the inflow of the given year to fill exactly that gap. So if the stock balance says we should have 100 because of the scenario, but we only have 85 left because of the lifetime model, we will produce 15. An example here is a 6x6 array for vehicles, since we also will have vehicles later in the exercise. What you see here is an age cohort by year table. The nice thing about the lifetime model is you not only know how much stocks you have, you also know how the stock is broken down into age cohorts. Like at every year, you know how many cars of the last year are there, how many cars of 2010, and so on. And this is important because every car vintage, so every car production year, has a different type composition. It has also different fuel consumption. For buildings, we know that buildings of different ages have different energy efficiencies. So we need to be able to keep track of that. And the stock-driven model gives you all this for free. So how does it work? What you see here in the left column is the years. It starts from -2, so this was 2 years ago. 0 is the present year, and then we look 3 years into the future. And we have a stock scenario. This is the second column from the left, showing a slowly increasing stock from 4 units 2 years ago to 6 units in the present year, up to 9 units in 3 years from now. And now we want to build up this model using stock-driven model. We want to build up the stock. So what we already know is that 2 years ago, we first introduced the product cars, so we needed to consume 4 cars. And last year, we had already 4 cars from the year before, and they were still in stock because the lifetime is 3 years fixed, so they hadn't reached the end of the lifetime. And to reach the stock scenario, 5 cars, we need 1 more car. The question is now what happens in the current year. In the current year, we still have the cars from 2 years ago because they haven't reached the end of their life. We also have last year's car because it's still there, but we need 6 cars and we have only 5. So we will consume 1 additional car more. So this is the additional 1 in the column 6 year 0, age cohort 0. And by following this rhythm, we can fill the entire table. You will see that in next years and afterwards, the cars from the first age cohort will be gone. This means below the first 4s in the left column of the table, there's 3 zeros because this first age cohort will be gone after 3 years. And you see that there is a shift. Every time the age cohort lives 1 year longer, but then it's also gone. So in the 2 years from now, the second last row, we have 1 car from this year left, we have 5 cars from next year left, and to meet the 8 cars that we need, we will have to consume 2 cars in the future. So you can see that you can solve the stock-driven model by hand just by filling out the table. Now imagine you have a big model, maybe 100 years, and maybe you have 10 different vehicle types, and you want to multiply material composition and so on. of course, the calculation by hand gets very nasty. And this is why we move to the software. So the next step, and this will be demonstrated in a minute, is how we can do exactly the calculation we just saw in a Python, in a programming environment, using some predefined classes. Before we switch to that, I want to give a bit outlook on why we're doing this and what are the next steps. I already mentioned one reason for moving from hand-based or Excel-based work to Python, and this is the efficiency. If you have big models, a lot of them, for example, you want to do Monte Carlo simulations, then of course it really speeds up your work. But there's also another reason, and this is that the software is very systematic. In the software, you write down what you do, and you can archive those scripts and share it with other people. It's much easier to share your work with other people if the actual steps are documented. And this is exactly what happens in the software, because every single calculation step is documented. Another advantage is that in the software you can write testing programs. So the methods I will show you in a minute, they have test routines. So whenever we make a change to the method, for example, we introduce a new lifetime distribution or we introduce a new export routine, we run the test. That means we check whether the model produces known results for known input data. And this makes the whole procedure more reliable. So when you use this method, you are sure that you get a model that has been A, used by many people, and B, tested many times. So you can be quite sure that it works. Whereas when you do your own modeling, you always have this insecurity that you first need to overcome. Another reason for using software is it can be linked to each other. It's easier to do cumulative science by building up on top of each other's work and also linking to each other's work. So one outlook that I want to give is the so-called material systems model. You probably know energy systems models. They have been developed for 40 years, calculating how humanity can meet its future energy demand cost efficiently and also in line with global constraints like carbon constraints or resource constraints. We don't have really such a thing for materials. And the reason is that materials are more complex because they're constantly mixed. You have different alloys, you have different ore deposits, and also materials can be recycled, whereas energy is usually just downcycled to heat. So when material can be recycled, and then you have again the mixing of alloying elements. And at the moment, we don't really have good models that can capture these different effects. So this is a long-term strategy that the software that I want to show you today will be part of, that we can, as a community, develop assessment models for not only single material cycles in the future that we have done already, but actually coupled material cycles, that we can ultimately link the service demand of future scenarios, like in terms of buildings and cars, to the material demand, for example, copper in battery electric vehicles, and then link this material demand to a model of the material cycle. How much copper do we need to produce? How much copper is sent to steel scrap because of bad recycling? And how much energy is in the system? So it's a way to systematize all these efforts and link the different material cycles together. There is a software platform that I'm not going to talk about today, but in case you're very interested, it is already on GitHub. So we are developing some basic accounting framework. If you attended the previous seminar on the LCA open source software, there was the complement between Brightway LCA and OpenLCA, and I think in MFA the situation is quite similar. We have a good analogon to OpenLCA. This is the Stan software that Oliver introduced last week that can do very good applications of standard LCA to help to get the method out into the practice, especially in the waste management industries. And we have the more experimental software, the Brightway equivalent, which here is called ODIM, the Open Dynamic Material Systems model, that we want to develop in a test field for using different scenario models and so on. We also have a general discussion on open science, sharing data, data standards, and so on, that invite you to have a look. And we have open teaching material, and what I'm going to show you now is also part of this course. So I have separate lectures on explaining more details of dynamic stock modeling and dynamic MFA in general, and there you can get more insights and also more exercises in case you want to get up to speed with this interesting and quite relevant method. With this, I want to switch to the practical part. In the practical part, we want to see an application of stock-driven modeling. What we want to do is we want to look at the population scenario for the global sphere, so the total world's population, and ask ourselves, how many materials do we need to build all the passenger vehicles in the future? So we have a case study on passenger vehicles. We use the system definition here. We calculate the total amount of vehicles needed as a fleet by multiplying population and the passenger car ownership for which we have a scenario. And then we calculate the inflow, that is the stock-driven model, and then we calculate the materials in the inflow. So let me end this PowerPoint presentation and switch to the software script. So I'll look at my different screen now, so away from you, and you should be able to now see an IPython notebook or Jupyter notebook. And Jupyter notebooks are a mix of text, pictures, and software, so that's a nice way of documenting your calculations. As I said, it's part of the Industrial Ecology Open Online course, so you can also find the data that we use and this notebook there. You can download it and try it out yourself. The research questions that we want to ask for this part is how much steel and aluminium will be consumed by vehicle manufacturers to build up the future passenger vehicle fleet. And we want to answer this question using stock-driven modeling. So what we do is we have a first model equation shown here where we say S is P times C. The stock of vehicle is the population times cars per 1,000 people. And for both P and for C, we have a scenario. From the stock, we derive the inflow needed to build up and maintain the fleet. That is the stock-driven model. So we need to do this later. This is just the equation. And then we will just multiply the material content of the vehicles to that inflow of vehicles. So how does it work in Python? What we need to do is first we need to import the modules that we need. We have the dynamic stock model that needs to be installed before, as explained above. We need NumPy for handling tables of data. We need a plot library, and also we need a library to read Excel data. So let's execute this part. And then we need the actual data. I'll show you how the data are organized. They're organized in an Excel workbook. You have the time dimension. The model goes back to 1950 all the way to 2050. So it covers both the history, where we know already the stock, and the future. We have the global population, actual population until 2015, and future population afterwards. We have the same for car ownership. We have the same for the average vehicle lifetime for each age cohort where the car was produced. We know how much aluminium is in the cars. It was roughly 27 kilos back in the 50s. And the scenario said it increases to 120 kilos in 20 years from now. The complement would be steel, roughly 960 kilos of steel. And this goes down quite rapidly until below 800 kilos some 20 years ago, and now it's rising again because the average global vehicle is getting bigger. So these are the data that are now read using this piece of code. So you see I open the workbook here using XLRD's workbook opener, and then I parse the workbook. Every column, the years, the population, and so on are parsed in a separate list. And the result here, the car alu content, for example, is just a list of numbers. So now we implement our equation to get the total vehicle stock. This is P times C. In Python, it looks like this. The total vehicle stock is the product of the two lists, population and car ownership, divided by 1,000 to get the unit right. And the car stock here, you see it was roughly 58 million cars back in 1950, up to more than 2.5 billion cars in 2050. So this is quite a lot. Current car fleet is roughly 1.1 billion vehicles. Okay, so now it gets interesting. We are now able to create our dynamic stock model. The dynamic stock model is an instance of the dynamic stock model class that was just loaded. So you see here, I have my global vehicles stock model. And To define this model in Python, I need to hand over the years. So this is the time series of years that we're using. I need to hand over my global vehicle stock, the time series that I want to analyze, and a lifetime array. Here I use a lifetime of type normal. So I normally distribute the lifetime with the mean of the car lifetime, so that's 16 years, and the standard deviation of 30% of the mean. So this is a quite common assumption we use in our calculation. And I create the stock model, and I checked its dimensions. So it tells me that there's a time vector of 100 years present, that the stock by cohorts is not present because we want to calculate it now, and the total outflow is also not present, but the lifetime is present. What I haven't done anything basically. All I have done is I take the data I have and put them into a nice container. And because the data are now in a nice container that has a method for computing the stock-driven model, I can now just with a single click, single command, call the stock-driven model. And you see it takes a while. There's still a star. And now it's done. So the entire stock-driven model is only one line of code. This is another nice part of the software. It can wrap quite complex functions into very simple code. So you get the stock by cohort, the outflow by cohort, and the inflow, just with this single line of code. And from once you have calculated those, you can also get the total outflow, the stock change, DS, and the mass balance over all the years. So let's now analyze the results. In case you're interested in what's going on in here, you need to go to the GitHub repository, and there you can access the source code. You can download it, and you can also modify it in case you find mistakes or you want to make the code more efficiently and so on. So the code that is behind here is available to everybody. What we will now do is we will take those results and extract them and analyze them. The first thing we do is to plot the global vehicle stock. And this is just a plot of the input results. So you see the stock is increasing 60 million, some in the 50s to more than 2.5 billion. So this is just a confirmation that the data are in the model are the ones that we put it in. And this is the actual model result. This is the central result here. It is the inflow and the outflow of vehicles that are used to build up and maintain the stock. And you see quite some interesting features here. So first of all, the stock also increases faster, and this means the consumption increases over time. There's more vehicles, more and more, and if the trend continues, we will need almost 200 million vehicles every year in 2050. So this is quite a lot. Then into more detail, you see there is this bump in the first year. And the bump in the first year is because we started with 0 stock in 1950, but there were already some cars. There were already 57 million cars. So the stock model just needs to build them all in the first year. It's a shortcut. And the reason why we do this is we are just too lazy to extrapolate the model even further into the past. And it doesn't matter because the 1950 vehicles have gone already. Most of them are not in the stock anywhere. So this bump doesn't impact our current fleet emissions and doesn't impact future fleet emissions either. So this is just a shortcut to cut the model to reasonable timeframes. And then the bump will just disappear after like 20, 30 years. Most of the cars will be done. If we would model the building stock until 1950, we couldn't use this shortcut because many 1950 buildings are still there and also elder buildings. So we need to go further back in time. You also see quite a few ripples here, and the ripples come from changes in stock growth. So these are actual economic crises you can see here around the year 2010 that can be seen in the inflow that are reproduced because the stock then also has slightly changed growth speeds. You also see that the outflow is always smaller than the inflow, meaning that the total stock is still growing. And you also see that there's roughly a 15 years time shift between inflow and outflow because this is the lifetime of the vehicles. So the inflow will kind of come back as outflow roughly 15 years later. We can also make a heat map of the age cohort year distribution. So the y-axis here is the time, and here you see the age cohorts, how they disappear over time. So on a diagonal, you have the new consumption, and then the stocks leave are for a certain time in the stocks, and then at some point they decline. And since the stock grows over time, the later age cohorts will be larger than the earlier ones, which is why there's red colors on the right side. Similar with the outflow by cohort. Outflow by cohort is the derivative of the stock change here. So you can directly see where the stock declines fastest, the outflow is largest on an age cohort level. We are now in a situation where we can actually answer the research questions that we posed, and we do this as follows. We first calculate the inflow of steel by taking the inflow of Wiegel, which is an attribute of the stock model, which was calculated with the method, and multiplied with the car steel content. So these two lines of code convert the inflow of vehicles into an inflow of materials into the vehicles. And once we have done this, we can plot the inflow of steel and aluminium into vehicles. And these curves have roughly the same shape as the inflow curve above, but not exactly the same. And the reason is that the steel content and the aluminum content of vehicles changes over time. So, but it doesn't change drastically. So you see the similar rough pattern, but it's not the curves are not exactly proportional. And you see here that currently about 85 million tons per year of steel are going into vehicles. That's roughly 5% of global steel production, so not so much. For aluminium, it's almost 20% of global steel production. So vehicles are a much more important market for aluminium than they are for steel. And we can also see how these curves and how demand changes in the future as the fleet continues to grow and the material content changes as we have it in our scenario. So this is the main answer to a research question, but we can, and this is a last trick I want to show you before we close the seminar, before we close the presentation, you can of course do more evaluation. One quite important question for the waste management is how much scrap is coming out. And to answer that question is we need to know how much scrap is coming in. So we can also, with our data, easily calculate the steel stock by cohort. So not the inflow by cohort, but actually the stock of steel in the different vehicle age cohorts. And there's a function that I really want to recommend you using. It's the Einstein sum convention. It goes as follows. We have a string here that says multiply two variables. One has a dimension t times c. T is year and C is age cohort, and the other one is a variable with the dimension age cohort only. And you multiply them together to form a T times C array, and the two variables to multiply are of course the stock by cohort and the car steel content. And this computation is very efficient, and it gives you directly the steel stock by cohort by just replicating the steel content across the different years for each cohort. If you know the NumPy tile function, this is the one that's behind here. So the Einstein sum convention is just a nice wrapper. We can do the same for the outflow. And then we can, for example, plot directly the steel content in the fleet. So this is now already quite a complex computation because we have different age cohorts with different material content. And here we can sum it all up together by multiplying each age cohort with its respective material content and then summing them all up. So to summarize both the lecture and the presentation, we saw how we can take a population scenario, a service scenario, for example here cars per capita, and calculate the inflow of products needed to build up and maintain the service. So this is called the stock-driven model, and we showed how this can be done very fast, quickly, and efficiently using a Python software that's freely available and that can be changed by everybody and extended by everybody. And we also saw how we can use that software to add the material layer to the stock by calculating the steel in the vehicle fleet and the steel in the inflow. And I hope that this presentation was interesting for you. The webinar will be uploaded at some point, and many slides contain links to paper where the methods is used, both the software and also the research questions are answered. And I hope that this presentation here made a few things clearer. Also remember there's this open online course that you can use, and there's more freely available material to try out. And I thank you for attention, and I'm very happy to answer the questions.
Thank you, Stefan, for your presentation. And we will now have a brief Q&A session. Thank you to those who have already submitted questions during the presentation. And as a reminder, if you have questions, please type them into the Q&A box below, which is not to be mistaken for the chat box, and I will go ahead and moderate the discussion now. Our first question is, Stefan, could you please provide some insights regarding which variables and methods you would consider to perform a sensibility analysis of the stock model?
You probably mean a sensitivity analysis. And I think this can be easily best shown by going back to where we define the stock. Do you still see my screen?
Yes.
So in this particular case, we have only two variables. We have the material, the vehicle stock, and we have the lifetime. So what you can do, I can actually do this online. I can just take these lines, copy paste them, and for example, say I take now a new stock 0.95 times the vehicle stock. So this means I can just copy paste codes and enter an alternative value and then redo the computations. So every variable that I have here in my system, I can just change. Either I change it manually by scaling the value, or I read alternative scenarios from the Excel sheet. And then I can recalculate the stock model and I can redo the plots. So that's quite easy here to do.
Great, thank you. And next question. Stefan, please tell us the advantage of using Python for such computations and compared to using a spreadsheet tool like Excel.
I mean, to be fair, there's both advantages and disadvantages. The answer is the bigger your model, the more variables you have, the more often you want to run your model, the easier it is with Python. If you want to do a very quick calculation just to confirm a few numbers, then of course I also use Excel. But when I want to write a journal paper and I want to have a proper Monte Carlo simulation and maybe I have 20 different parameters, then I will use Python. And the reason is that with Python, with a script, it's very easy to make changes. As I showed you here, you discover you want to make an alternative, so you just do copy paste. You copy your old code, paste it into a new version, and you compute the change. So my experience is as soon as you have more than 50 years, like model years, and as soon as you have more than 5 parameters, it's worth making the effort switching to a programming language. Doesn't have to be Python, but for Python we have already tools available. And the good thing is once you can do this, it's much easier to go fancy. For example, doing Monte Carlo simulations or doing a lot of different scenario calculations and sensitivity analysis, plus that Python also is much better at making nice plots than Excel is.
Thank you. And the next question is, you provided examples based on the global passenger vehicle fleet. Do you think this can be applied to any other industries, or do you recommend any industries that this kind of analysis be applied to, and how do you see it playing a role in promoting circular economy and sustainable development worldwide?
The first question is, it's actually done already. It is done by most people that model material cycles. So we have also dynamic stock models for buildings, for infrastructure, and for products. And if you think about the wider community, for example, integrated assessment models, they also have dynamic stock models. The best example is the energy sector. If you want to compute a future energy scenario, you can't just have a clean table every year. You need to respect the lock-in that you already have power stations up and running that were built the last year. So if you make an energy scenario, for example, what is the energy mix of 2020, you need to take into account that there are already power stations available that were built 20 years ago and that they're still operating. So this constraint is handled by a dynamic stock model. So it's commonly used across scenario modeling in all fields that link energy to emissions, because the link is actually done by the stocks. And the second question regarding sustainable development goals and circular economy, I think it's crucial to understand the inertia that the stocks present. For example, in China, 98% of the steel consumption are put into growing stocks and not into maintaining stocks. Because in China, the stocks are still expanding. And you cannot have a circular economy if your stocks are expanding. So the perspective that the stock modeling offers is to better understand under which conditions you can go circular. And one answer is, if the stocks are still growing, there's no way of going circular, because you need to have primary production to expand the stocks. You can only recycle if you have stocks to recycle from. So it's a new perspective. It's not new, it's an additional perspective that complements the picture and helps that we are not too simplistic in our thinking when it comes to circular material flows.
Thank you. And the next question, could the wrapper function be easily extended to consider more heterogeneous factors, for example, considering various countries or running stochastic simulations?
Yes, I can also show you this. In Python, this would work the following. You create a for loop, let's say for m in range 0 to 1000. So you can just loop over your stock model, and every time you do this, you can have a different m. For example, a slight random variable. So this would be 0.95 times mp.random. Sorry, random. And then this would create a random variable that simulates a Monte Carlo simulation just within a loop. The same you can do for countries. So you can say maybe not 1,000 Monte Carlo runs, but number of countries. And then here you don't do this random number thing, but instead your vehicle stock is now a big table and it comes from the country index. So the loop index is now taken here, right? So you have maybe not one car scenarios, but you have one car scenario for each country. So you can just loop over them. That's another nice advantage of a script. It's very easily scalable.
Great. And can you please explain which types of lifetime distributions are currently supported by the dynamic stock model and how custom distributions can be applied?
Yes, currently we have implemented fixed lifetime, a gamma distribution, and a normally distributed lifetime. And to add a new lifetime, you would need to go into the source code behind this software. And it's essentially one line of code that you need to add. And the line of code is just that you need to tell the software how to calculate the values that you give here into the lifetime distribution. And it's predefined, so Python knows a lot of lifetime distribution. You just need to select the right one. What takes effort is that you also should test. I mean, it's easy to make changes, but you also should write a test routine so that you by hand calculate what the result should be, for example, for a Weibull or a log normal distribution, and then make sure that your calculation actually does what it should.
Thank you. And the next question, how does an inflow-driven model with historical data can be connected to a stock-driven model for future scenarios?
That's a good question, because this is the proper way of solving this bump problem here. But I don't want to talk about this now because it's a bit technical and there's material on it. So what I want to show you is, if you go to our open online course, of which the link you saw in the previous slide, there is in the section 3, there is a methods methods section 3 software 1 where we exactly show how this problem is solved. Basically, the method can take an extra array that contains the historic stock, and it will then use that historic stock. Just to keeping the seminar today short, I didn't include it here, but there is a specific exercise showing exactly how this is done.
Thank you. And another question is, how long can stockpiles be stored?
This I don't understand. Is it like maybe how many years you can run the model for? And the answer is as many as your computer fits into the memory. So, for example, I had this plot I showed you before on the lifetime of steel. I had a dynamic model that ran into the year 3000, so 900 years from now, because steel is a very long-living product. So I actually did a 1,000-year model with a 1,000-year time horizon, and that worked also quite nice. And your lifetime can also be of any length. In many European countries, we have residential buildings with a lifetime of several hundred centuries. The same for many buildings in India, for example. And this can also be done. That's no problem.
Great. And there are no more questions. So unless anyone else has last thoughts, go ahead and please type it into the Q&A box. Stefan, any last words you would like to say?
I'm just happy that it went through smoothly and no software crash from my side. So thanks a lot, everybody, for attending. I hope it was interesting. I hope the material that is out there will be helpful to you. And please contact me if you have specific questions or any other issues you run into. So thanks a lot and have a good weekend.
Great. And with that, we conclude today's talk on dynamic MFA with Python. Stefan, thank you so much for joining us today and for the participants as well. To view a recording of this webinar, please visit the member portal of the ISIE website. Thank you, everyone.
Bye.